So this is our stress X, just for example, okay? And then we have our stress Y. And then we will have our shear. So I'm going to put our shear somewhere around here. Okay, so this is our shear stress. So this is our shear XY or shear YX, either one, okay? And then from here, we know at this point over here, this is our point Z. Okay, this is our point Z. And based on the element rotation, so element rotate clockwise. Sorry, on X, element rotate anti-clockwise. And then this is our Y. Then from here, we can sketch our mole circle. Here we can sketch our mole circle. So I'm just going to briefly sketch. So that will be (2.2). So this is our mole circle. This is just a sketch, okay? All right, mole circle, not mole square. Okay. So this is our mole circle now. Okay. So what we have drawn down here, so this is for not very precise, but I'll try. It's a bit overish now. I think it's way too high. Okay. So this is for our XY plane, right? And then we can construct another circle over here. And now this is for our XZ plane. And then our third circle, so 2, 4. So it's going to be somewhere around here. So that is our third circle now. So this circle over here will be for our YZ plane. Okay. So what we realize down here, right? Under this condition, what I'm trying to show you is this. Why did we assume, okay, why did we assume that stress B is equal to 0, right? Okay. So you can see now over here, this is our stress A. Okay. And over here, which is our stress B, our normal stress B, you can see for the fact that it's equal to 0. This is because we assume it to be what? Plane stress, where stress Z is equal to 0. That is why this assumption where stress A equals stress U, stress B equal to 0 is valid. Okay, so I'm trying to show to you why stress B is equal to 0. Okay, so based on plane stress condition now, okay, based on plane stress condition now, equation 1 becomes, okay, so equation 1 is this equation over here. So we let stress B equal to 0. So what we have now, right? What we have now is we are going to consider the energy, the distortion energy at U now. Okay, now we're going to focus at U now. So this is equal to 1 over 6G, right? And then you have this is equal to stress Y squared minus by stress U multiplied by 0 and then plus by 0 squared. Because we assume what? Stress B is equal to what? 0. And stress A over here, we're going to put it at stress U. So that is why this equation from equation number 1 is the distortion energy at U, because we are assuming that stress A is equal to stress U. Okay, so from this case, we know that based on the maximum energy distortion, we have the expression will simplify itself is equal to stress U squared divided by 6G. Okay, so this is what we call von Mises yield criterion. Okay, that's why we call von Mises stress yield criterion. So the structure is safe. So how do we apply this criteria? Okay, so to apply this criteria, the structure is safe based on energy comparison now. Okay, so the structure is safe okay, we classify the structure is safe when the distortion energy during the analysis is less than the distortion energy at where? U. So this is calculated based on structure analysis, doing structure analysis. And this criteria or this condition over here is a material property. Okay, it's a material property. So we are going to combine equation number 1, right? Equation number 1, and we're going to combine what we have written before over here. This is our equation number, our von Mises criteria. This is our equation number 2. Okay, so when we combine these two now, okay, so we write down an expression where we have 1 over 6G, right? And then you have stress A squared minus stress A stress B plus by stress B squared. And then this whole thing will be equal or has to be less than 1 over 6G, and this is multiplied by stress U squared. Okay, so we know that we have common term on the left hand side and on the right hand side, right? You realize that we have terms that is equal to our left and to our right. So in this case, you can get rid of them, right? So we'll have an expression where we have stress A squared minus by stress A stress B plus by stress B squared, and the structure will not fail if the entire equation on your left hand side, which is from structure analysis, is less than stress U squared. Okay, so you realize on the left hand side, this term over here, stress A and stress B are not equal to what? Are not equal to 0. Whereas on the right hand side, stress U over here, how we get this expression over here, like the previous assumption that we make, is where we have stress B is equal to what? 0. Okay, right. So now let's look at this term over here. Let's focus on this term down here now, where stress A squared. Okay, let's look at this term down here. So if you look at over here, the parent function, right? The parent function will be is very similar to x squared over a squared plus by y squared over b squared is equal to 1. Can anyone tell me what is this equation? Have you seen this equation, an expression like this before? Anyone? Anyone? So if you were to look this is a ellipse equation. If you want to draw an ellipse, okay, where x is your x-axis, y is your y-axis, a and b are your constant, you have an ellipse. Okay, so if you were to expand this equation, okay, so you have b squared x squared plus by a squared y squared, and this will be equal to the common denominator is a squared b squared. This is equal to 1. So you have b squared x squared plus by a squared y squared is equal to a squared b squared. Then finally you have b squared x squared minus a squared b squared plus by a squared y squared is equal to 0. So the parent function, right? So you have your x squared down here, y squared down here, right? So this parent function can be used to describe our expression over here. Okay. So when we plot our graph over, when we plot stress a squared minus stress a stress b plus by stress b squared, how does it look like? Okay. So what I'm going to do now, I'm going to sketch both Tresca and von Mises, and I'm going to put them over one another. Okay, so here we go. So first I'm going to sketch Tresca first. Okay, so I'm going to sketch so this is our stress A axis, and this will be our stress B axis. Okay, so this is stress A axis, this is stress B, and over here this is our stress U minus stress U. This is our stress U. And last week we explained why the expression is like this for Tresca. Okay, so we're going to draw Tresca first. So this is Tresca's. So anywhere with any point of stress A and stress B condition within this boundary that I'm drawing, the structure will not fail. Okay, we talked about that last week. And how does it look like? Okay, so now, so this is our Tresca. So if we were to sketch von Mises, right? If I'm going to sketch von Mises, now use a different color. So if I'm going to sketch von Mises is looking like an ellipse. Okay, so I'm trying to draw an ellipse now. Okay. This is a sketch, by the way. Okay, it will not be perfect. Right. So what I've drawn in red, this is known as Tresca. And you realize that, no, von Mises, hey, wakey, Eugene, you're sleeping now. So this is now our what? Von Mises criteria. Okay, now we will see. So there is some similarities for von Mises and Tresca, and there are some differences. Okay, so now let's look at. So I'm going to call different points now. Okay, I'm going to call this point A. Or yeah, I'm going to call this point A. I'm going to call this point B. Okay, and I'm going to draw a line over here. Right, I'm going to draw a line over here now. Okay, so this will be our point C, and over here our line C, point C, and this is our point D. Okay, that's our point C to point D. So we're going to look at the stress state now. Okay, we're going to look at the stress state now. So where are the similarities? Okay, for both Tresca and von Mises. So von Mises, and then we have Tresca, Then we have our point A. We have our point B. We have our point C. And we have our point D. So at point A, right, what we see that for von Mises, stress A, point A, and stress at point B, both are at the yield. For Tresca, it's the same. Stress at